Hello there and welcome back to this video series on control systems. Over the past few classes, we have been writing equations for individual sections of an armature controlled DC servo motor, and in that effort we built the overall block diagram, and we have seen that in the overall block diagram there is an inherent feedback loop. After watching this video, you'll be able to specify how the steady state torque is related to the steady state speed in an armature controlled DC servo motor. We'll do that, of course, under a couple of reasonable assumptions. To do that, we'll begin by looking at the schematic of the DC servo motor. This is the armature with two brushes and armature terminals, and we have the motor shaft connected to the armature, carrying a equivalent inertia and equivalent damping, and we have armature resistance to be Ra, inductance to be La, and a voltage of Ea applied there. Along with that, you have field windings which generate magnetic lines of flux, which when they cut the current carrying conductor, you have a torque developing. When torque develops, motor moves. When all this is happening, you have certain back EMF appearing. This back EMF, we recall, opposes the applied voltage. With this setting, we will try to indicate the nomenclature that we use, which is as listed over here. Carefully go over this. We saw that this is the overall block diagram with two inputs, applied voltage and the disturbing torque. Okay, recollect that the torque equation is Tm is equal to Td plus J equivalent into S into omega m plus B equivalent omega m. We'll come back to this equation once again. We saw that this is the equation. We have one transfer function G1s relating omega m and Ea, another transfer function G2s relating omega m and Td. Carefully note that the second transfer function G2s has a negative. Okay, that would mean when Td is increased, the omega m is decreased. We will note two aspects here. When motor is very highly efficient, the back EMF constant Kb and motor constant Km are approximately equal. So you get, instead of Km Kb, you get Km square. Similarly, the inductance in the motor coil is very small, so we neglect this La, we neglect this La, we neglect this La. Under these assumptions, this equation can be reduced to what is shown over here. We slightly try to manipulate it to get to the transfer function in the form we require after doing a little bit of algebra. Rearranging this term, we get this. So the first thing we obtained was that the expression for motor torque is given by J equivalent Ra divided by Rab equivalent plus Km square. We try to further look at this equation and see what happens at steady state. We know from the Laplace transform, initial value and final value theorems, when S tends to 0, it would mean steady state. We'll try to use that concept and say that we can get the steady state values by setting S tends to 0. Under these conditions, let us represent omega with a subscript SS steady state to represent steady state speed, which is steady state torque, and steady state voltage applied. With this, the equation simplifies to what is shown over here. Okay, we slightly rearrange the terms to further bring the steady state motor torque TSS into picture. So we'll try to see how this term can be eliminated. We see that for the load section, motor torque is disturbing torque plus J equivalent to S plus B equivalent into omega MSS. Okay, omega steady state. If you substitute S tends to 0 here, this term goes away. So, and this term is TSS. When S tends to 0, all the quantities are steady state quantities. So this is steady state torque plus whatever is this. Notice carefully that this term and this term are identical. Because they are identical, in this place we can substitute TSS. So this seems to be the equation relating steady state torque to the steady state speed. We are interested in defining what is rated speed. We say rated speed is the speed of the motor when power developed is maximum. To that extent, we write what is the power developed, which is torque multiplied by the speed, and we differentiate it with the speed, set it to 0 to find out the condition for maximum power. When you substitute this to 0, you get such an equation from which you get the steady state speed for maximum power is given by this. It is this quantity which is called the rated speed, and this is the quantity perhaps that is printed on the nameplate of the motor. At this rated speed, we can find the torque, rated torque, as given over here. Okay. Seen that this equation is of the form y is equal to some constant c minus the slope into a variable. So this is of the form y is equal to c minus mx. We note that and draw the characteristics as shown here. Along x-axis, we have plotted the steady state speed. Along y-axis, we have plotted the steady state torque. And we note that this equation has a negative slope because we have minus k to omega m. Okay, so the line is a negative slope line. And this point where torque is equal to 0, this is x-axis. So y is 0, y is the steady state torque. So this is called no load speed. Similarly, this point is called stalling torque. At this point, you have speed is equal to 0. Call this point A. At point A, you have speed is equal to 0. Using that, we can get stalling torque value. Substitute omega SS is equal to 0. So TSS is equal to K1 into ESS. This we call stalling torque, and we see it is twice the rated speed. Similarly, at point B, which is here, we see that the torque is 0. When you substitute TSS is equal to 0, this omega 1 you can find as K1 over K2 into E, which is twice the rated speed. So midway between the line, somewhere indicated here, you have maximum power. This power, the speed is no load speed by 2, and torque is stalling torque divided by 2. This point is the point which refers to maximum power. We'll stop here and summarize what we have seen. Time constant of the armature controlled DC servo motor is derived. We later derive time constant for the field controlled DC servo motor, and we see that armature controlled DC servo motor settles faster. Okay, the torque speed characteristics are shown to be linear, and we saw that rated speed is half the no load speed and rated torque is half the stalling torque. That's all we have for today. Have a great day.